Audio Jungle. Audio Jungle.
Hello everyone. Here in this video we are going to discuss about Kirchhoff's laws. Kirchhoff's laws means both KCL as well as KVL. First we will see for the word KCL, that is Kirchhoff current law. KCL is applicable for any node. Any node means we classify the word nodes into two categories like simple node and principal node. What is the difference between simple node and principal node? Simple node is nothing but it is a point or junction where two elements are connected. Got the point? Simple node means it is a point or junction, only two elements are connected. When it comes to the word principal node, more than two means definitely starting from what three elements generally. So principal node means it is a point or junction where more than two elements means like 3, 4, like whatever it is, then we call that point or junction as what principal node, right? So KCL we can write for any kind of its node, okay, right? Not only simple, we can even apply for the word principal node also. Now when it comes to the statement, here I am explaining statement, again we'll write on the board also, right? Then we'll take some sample example, then how we are writing we'll see. That is the objective for this KCL now. Statement, if you see, generally both KCL as well as KVL we write only for what lumped circuits or lumped network. So how we write the statement here? In any lumped network for any of its node, okay, the algebraic sum of leaving currents is 0. Okay, so it is a basic one, okay, conventional statement we are writing. So what is the statement here? Statement, in a lumped network for any of its node at any instant of time t, right, the algebraic sum of leaving currents is 0. Okay, this is the statement, right? Now when we take a sample example, okay, sample example means like a node we take and it consists of several branches, then how we get the word relation we will see. First, suppose if I am considering this node, okay, and I am assuming some branches. Okay, I am not giving any information like consists of a voltage source, current source, or like RLC components. Simply, I am indicating only currents in that each and every branch, because our intention is only for the currents we are showing here. Understood? Suppose if I am now selecting some incoming as well as what some outgoing branches here. I am showing with currents like I1 here, okay, like I2, I3, I4, I5. Now for this node, when I am writing the word KCL, look at here, algebraic sum of leaving currents is 0. Algebraic sum means we are just adding all the incoming as well as what outgoing currents. But polarity must be different because we are going with algebraic sum, plus or minus we take. Okay, how we take the notation here? Suppose if you are choosing positive sign for incoming currents, then outgoing currents or leaving currents must be what? Negative. vice versa. You can choose any polarity, absolutely there is no restriction, there won't be any change in our result also. Suppose if I am following with this procedure, okay, every time we'll be doing the what direction as well as what even polarity with this procedure. What is that? I am keep on choosing the same notation here. Incoming current I'll choose with what negative sign, outgoing current we choose that what positive sign. This is the procedure we follow in all these examples, okay. Whatever the position, like we discuss the what any topic we follow with this kind of notation, right? Incoming I am choosing what negative sign, outgoing I am following with what positive sign. Now just impose the what KCL for this node. What we get, okay, incoming current, algebraic sum. Incoming means I1 is incoming, so minus I1 I am writing. I2 is what outgoing, so positive sign because it is algebraic sum. Again I3 is what incoming, so minus I3. Next, if you look at that, both I4 as well as I5 both are what leaving current, so plus I4 plus I5 which is equal to 0. Same thing, okay, right? Algebraic sum of leaving currents is 0, then incoming must be what opposite to that. That is the reason why we selected this notation. You can even write, okay, incoming currents into one side, outgoing currents into another side. Then what we can have, I1 plus I3 which is equal to I2 plus I4 plus I5. Look at this, what we can even observe from this. At a node, these are what incoming currents, these are what leaving currents. So what you can come in, not only algebraic sum of leaving currents is 0, you can even say that at a particular node, okay, at any instant the sum of incoming currents must be equal to what? Sum of outgoing currents. Okay, that statement also you can write. Another way you can observe here, the sum of incoming currents is equal to the sum of outgoing currents, right? And some more observation we follow here. What is the current? Current is nothing but what? Rate of flow of charge or electrons. So we simply replace that I is equal to dq by dt, that mathematical relation here. Then what will be the expression we get here? I1, I3. In all these currents, when we use this mathematical relation, we can write it as what? dq1 by dt plus dq3 by dt, which is equal to dq2 by dt plus dq4 by dt plus dq5 by dt. So both sides you can take d by dt common, you can cancel. Then what we get? q1 plus q3 is equal to 2 plus 4 plus 5. Like this you can write. So what is the observation from here? At a node, at any instant, sum of incoming charge is equal to sum of outgoing charge. And one more observation, you can even replace charge is nothing but what? N into E, where N is the what? Number of electrons, E is the what? Electron charge. Each and every electron will have the what? Same charge. What is the electron charge? 1.602 into 10 power minus 19 coulombs. That will be same for every electron. Only number of electrons in the corresponding branch will change the what will be the charge in that branch. Okay, so from here if you replace only electrons, that is number of electrons is changing, so E you can cancel both sides. You can even write in this way. I am putting R, so N1 plus N3 which is equal to N2 plus N4 plus N5. So what is the point you can impose here? At a node, at any instant, sum of incoming charge or sum of incoming electrons is equal to the sum of outgoing charge or outgoing electrons. That statement also you can add it to this. What is happening here at a node? Incoming charge is equal to outgoing charge means node is neither creating nor destroying what any amount of charge. So what we can say from this statement here, KCL is what associated with what? Law of conservation of charge. It is neither creating nor destroying, it is just passing, okay, right? Incoming charge is equal to outgoing charge you are saying. So what is the observation here? Observation we are writing like this, okay? Observation I am adding at this position. First one, KCL is associated with what? Law of conservation of charge, right? That is the main observation from here. What is another observation? Look at here, as I said earlier, starting when we took this sample example, means a sample network with these branches, we didn't mention what kind of element present in the respective branches. Got the point? We simply just indicated with only currents like I1, I2, I3, whatever it is. Okay, in this respective branch we might have the what a source. It could be voltage, current, or else any one of this. Source means it is an active element, or else means passive element. Sometimes we can even have a diode also. So all these are what different type of circuit elements, but still you can apply the word KCL. Understood? So what is the observation you can give? KCL is what? Independent of nature of the circuit element. KCL is associated with law of conservation of energy. Another observation is what? KCL is independent of nature of circuit element. Nature of circuit element means we may have active, passive, like linear, non-linear, bilateral, unilateral, whatever the kind of element, but you can even apply the word KCL. One more thing, KCL is strictly applicable for what? Lumped networks only. Understood? These are the observations when it comes to the word KCL. Now we'll look into that another Kirchhoff law, that is KVL. Okay, first we'll see that statement. Right? Here also we are writing KVL for lumped circuit only. In a lumped electric circuit, the algebraic sum of voltages in a closed path is 0. Right? You can take any closed path. Okay. Further closed path, when you write the word like algebraic sum of voltages must be what? 0 in that closed path. Right? Once again I am repeating here, in a lumped electric circuit the algebraic sum of voltages in a closed path is 0. Now here I am assuming one sample lumped circuit, means one closed path I am choosing in that. Okay, here I am placing a voltage source, right? Elements like resistance, inductance, capacitance, even I am placing a diode here. Okay, only one closed path you can find here, like RLC diode. I am placing some notation here. Okay, RLC, three elements are what? Linear, bilateral, passive components. Okay, diode is just a switch here. Means in forward bias having some resistance. It is just acting like a passive in forward bias. Okay, right? Anyway, here also we mentioned that diode is in this forward bias mode, having some internal resistance, so some drop will be there. Now when we write the word KVL for this closed path or loop, you can call, Anyway, if you just identify the polarity, how to write, okay, right, algebraic sum of voltages. Very basic onwards we are giving the polarity here. Observe here voltage is there, plus minus. When I choose this passive elements like R, L, C, these are what bilateral. You can choose direction of the current in any manner here. So if I choose the direction of the current in this way, suppose I am choosing this current I in this fashion. So passive element means these are absorbing, so definitely current flows from what? Entering into the what? High potential. Based on that, this must be the what? Polarity for each and every element in this closed path. And again I am indicating that some voltage drop across each and every element. So resistance means VR, inductance means VL, capacitance means VC, diode means like VD I am taking. Now if you write the KVL, algebraic sum of voltage in a closed path is 0, means if I choose the path, current entering into this negative terminal, so I am placing what? Negative sign, minus V. So current entering into positive terminal, so I am placing what? Positive sign. Absolutely there is no restriction, okay. You can even take for this positive sign, then definitely negative sign must be there for this, but I am following with this current direction. So based on the current direction I am giving this polarity here. So current entering into negative terminal means negative sign, entering into positive terminal means positive sign, that is plus VR, next plus VL, next plus VC plus VD. All these are what? Having some internal resistance, some drop will be there here. So I am writing voltage drops, okay, algebraic sum of voltages in this closed path. Now if you write source voltage or supply voltage one side, remaining will be like VR, VL plus VC plus VD is equal to that one. Okay, now what is basic definition of the voltage? Voltage nothing but amount of energy required in bringing the what? Unit charge from infinite distance to the what? Specified point. Applying the voltage is nothing but what? Giving energy only. So in a closed path you are giving some energy, then that energy must be what? Utilized by the what? Other elements in that closed path. So this is the amount of voltage you are giving. So that voltage is utilized by these passive elements. So energy you are giving, these elements are what? Utilizing. So in a closed path, energy neither created nor destroyed. Some elements are delivering, remaining elements are what? Absorbing. So what is the main observation here? What is the main observation? Kirchhoff voltage law is associated with what? Law of conservation of energy. Okay, earlier KCL is what? Associated with law of conservation of charge. Now it is associated with what? Law of conservation of energy. Again another important point, what is that? If you notice this closed path consists of a source, means active element. Here these are what? Passive elements, means linear passive element. It is non-linear, again passive element. All the combination is present. So you can apply the KVL for any kind of element present in the closed path. So you can even say that KVL is what? Independent of nature of circuit element, right? But again it is also applicable for what? Lumped circuit. So what is the conclusion from this? Both KCL and KVL, both are applicable for what? Lumped circuit only. Again both are independent of nature of the circuit element, but KCL is associated with what? Law of conservation of charge, whereas KVL is associated with what? Law of conservation of energy. This is the difference in between both.